Hello.
Yes, yes.
Okay. So let's start. The first means, this tutorial sheet is already forwarded to you. So uh, we will start discussing on that. But first, start recording. Okay, it is already started. Huh. So the first problem. So anyone has any doubt here? Hello. Have you tried to solve this problems? Hello. Hello. Okay, if you will not say, then maybe I will ask.
No, sir, we did not. I did not try, sir.
Hello. Hello.
Yeah, sure.
Ah. Okay. Then let's start problem number two. It seems that no one has any doubt in question number one. Problem number one. So first read the problem number two. Okay, so let's read it together. The datasheet of an IC accelerometer sensor ADXL335 is attached. Okay, so I have taken this separate PDF for that. Okay, so here the specifications of the data sheet is of that instrument is given. The basic description of the sensor is given in page 1. The sensor specification parameters are given in page 3. Assume a particular sensor having the typical values of specification parameters mentioned in page 3 is used to measure the acceleration sensed during single axis motion of a body. Assume the sensor to have a bandwidth of 10 Hz and the supply voltage Vs to be 3 volt. Interpretation of bandwidth, noise statistics, etc. are given in page 11. Assume an ambient temperature variations in the range 5 to 45 degrees centigrade. Assume the acceleration of the body to be limited in the bandwidth to less than 0.5 Hz. It is it clear? Hello.
Hello? You were not audible in between for some time.
Okay. So what I am saying that in this read this problem number 2 and then directly refer to the page number 3 of the instrument specification and try to make sense of the parameters which are given and try to relate it with the theory class, means the concepts which you have learned in the theory class. Okay, so what is its range, what is its specification, which is the modifying input, which is its interfering input. So first read it, then I will share this data sheet. Then you can make sense. We will discuss on that data sheet in the next part. So is the this statement clear to you? Hello, am I audible?
Yes, sir.
So now, before going into the data sheet, let's see that what is asked from here. That is, first thing is that calculate a specification of the total measurement error of the sensor under the conditions of the usage mentioned as X% of.
Sir, you are not audible.
Okay. So here you have to find all the specification parameters. Sorry.
You are not audible in between.
Oh, what is happening? Am I audible now?
Yes, yes.
Okay, so define all the specification parameters. Means here you have to find all the parameters related to those static characteristics. Means this k, all these things you have to find. Okay, so is it clear? This problem number 2 is apart from the data sheet and how to understand and interpret that data sheet. What is being asked means what you have to find. Is it clear?
Yes, sir.
Okay, so let's go to this problem sensor specification. Okay, so this is the general description of the sensor. So this is an accelerometer, 3-axis accelerometer. uh, Means here you can read that some things has already been mentioned in the problem sheet. Now I am directly going into this problem number specifications. Okay, so here it is given that the ambient temperature is 25 degrees centigrade and the supply voltage is 3 volt. And here are the three capacitors which are connected. Its value is 0.1 microfarad. Okay.
Yes, sir. Sir, you are not audible. Hello, sir. अरे Sir, you are not audible.
Probably he got disconnected.
Hello, am I audible?
Yes, now you are in between. It is cut.
Okay. Nishant? Nishant, are you there?
Hello.
Yes.
Yes, sir, you're audible.
Okay. Nishant? Okay. Okay. Akshit?
Yes, sir.
Okay. So try to interpret the first specification which is given. Measurement range. Okay, so here it is given that this is all these specifications are for each axis, because here in the problem description it is mentioned that the acceleration is sensed during single axis only. This thing we have to keep in mind, and all the specifications here it is given for each axis. Okay, so what do you interpret? How do you interpret this? Measurement range. Is it an input signal or output range? Hello. Hello, am I audible?
Yes.
Orko Prabha, are you there?
Yes, sir.
Huh. So,
Yes, sir.
okay, can you interpret this thing, that what do you mean by this measurement range, and from the values given here, what you can interpret means what is?
Sir, it is the average value it is taking is 3.6 G, and the minimum value it is going to 3, and maximum is not specified.
No, so the first thing we have to understand is that is it input specification or output specification? Means the sensor has two part, one is input and another is output. So is it input specification or input limits range or output range?
It is written sensor input specification. So
Yes. So this is input specification. So here the acceleration is the input and the output is in terms of voltage. So the range means that the values will be measured from what value to what value, means the minimum value and maximum value. So the typical value, that will be measuring is that from minus 3.6 to 3.6, and it has some minimum tolerance, because these are some sensors which has some various variants. So here in the
Sir, you are not audible.
hello, am I audible?
Sir, now you are audible, but in between you are not.
Yes, actually I am facing some internet issue. I don't know why. Because I am in campus, still I am facing it. Okay, so is it clear to everyone? Okay, can I proceed to the next part? Okay, the next part is non-linearity. So the non-linearity means, let's take the answer from someone. Krishna. Krishna, are you there? Hello. Okay, Moinak. Hello. Hello.
Yes.
Okay, so here in the input sensor input specification, the non-linearity is given that its value is full scale value. Okay, so from here you can find out that means what is its value. It is already given, means here the in terms of if you will see the question paper, that the census error specification, we have to find X% of full scale output. So full scale is actually 3.6. So that 0.3% of the full scale is the total nonlinearity error. Is it clear?
Yes, sir.
Okay. The second error is that the package alignment error. Okay. So means what is this package alignment error? So you can try to answer that what is package alignment error, and from this specification how you will interpret it. Means how we will calculate this error, or how this error will be will affect the actual reading. Rohit? Hello? Hello?
Yeah, sure.
Okay, so the package alignment error, that is actually related to how the sensor is actually placed in the alignment error thing. So if the alignment error is given some x degree, then from there we can calculate that if the value is, let's say, x, then and the alignment error is theta, then what is the component of that acceleration, x g acceleration, in the reference x with respect to reference axis, you have to calculate. Is it clear that means how this package alignment error will affect the actual measurement? Hello?
Yes, this is a problem.
Yes, sir. Yes, sir.
Okay, so means if you are measuring some quantity, then you have to find its component in the reference axis, and if after means calculating that, you will see that there is some discrepancy if it is not aligned in that reference axis. So that error you have to calculate. Okay. So the next error is the inter-axis alignment error and the cross-axis sensitivity. Now, as we have in the problem description, we have already seen that we are only dealing with the single axis motion. That's why this inter-axis and cross-axis sensitivity.
Yeah, I just want to say that if the unidirectional acceleration was not aligned with the axis, then it would have come. If it is between x and y. If you understand what I'm saying. Am I audible? Do you understand what I'm saying? That if we
To
assume,
find
yeah, please go ahead.
in the problem number A, it is mentioned that we have to find this error with x% of full scale output and y% of measured output. So the error has two components. One is some fixed error, that is with respect to full scale it is specified, and another error is specified in terms of the measurement, in terms of measuring input. Okay, so that's why as we have seen that this is with respect to full scale, but how this is specified?
Yes, sir.
Is it with respect to full scale, or is it with respect to value?
So it is given full scale.
The non-linearity is given with respect to full scale, but I am talking about the package alignment error.
So it is about respect to value because unit is given degrees.
No,
Sensor.
no, no. So suppose that there is a marked x-axis. Actually, you know, Suranjit, for taking class, this tablet is. I mean, we have to. Problem is that we are not able to write. So let me write.
Okay.
So realize that whoever is going to take tutorial should be able to write. So you can use this. What is that called? Google One something. Yes. There's some board, a whiteboard type thing you can use, na?
Yes, sir.
So use it. Otherwise, you will not be able to explain anything. Let me just see whether I can write something here. Okay. Hold on, I have not yet presented my screen. Okay, let me present the screen just quickly to understand this error. Are we doing it? Hold on. I'm presenting my screen, huh? Okay.
Yes, sir.
Hold on. Yeah, can you see my screen now? Yeah. So let's go to whiteboard. New tab. So yeah. So suppose the acceleration is, let us say, this is the marked x-axis, and the board, that is the sensor axis, is aligned like this. This is theta. The maximum value of theta can be 0.1 degree. So if you are applying this is inside the sensor, so you don't know. Imagine that the sensor has a box. On the box, x-axis is marked on top of the box, but inside the box, the sensor package is misaligned. It's not marked. It is not aligned with the marking on the box. So you have mentioned, you have installed the sensor marking this as the axis, say z axis. But inside it, the sensor is a MEMS sensor. So the sensor inside the package is actually aligned along this. So then, if you have a, say, an acceleration A, an acceleration AZ, then the sensor will sense AZ cos theta. There are two other sensors. So there is another sensor here, another sensor. I'm drawing three-dimensional here. So the other two sensors will also produce two outputs because of cross-axis sensitivity, but we are not bothered about them. We are only taking this output. If the measured acceleration, if the acceleration that we are trying to sense would have been along a general arbitrary axis in 3D space, then we would have had to take AX, AY, AZ, all three of them. And then A would have been, magnitude of A would have been root over AX square plus AY square plus AZ square. So then the cross-axis sensitivity will now come into play. But since we are in the problem, what is given is that the actual acceleration is happening along the marked axis and the sensor package is misaligned. So we are only concerned, we are only taking this, using this measurement. The other two outputs are also being produced due to cross-axis sensitivity, but they are not used. Because I am assuming that the acceleration that I am trying to measure is supposed to be aligned with the z-axis. So I am only interested in AZ. So is this clear now? Yeah, somebody is calling. Huh? Okay. Hello. Okay. You guys go ahead. You can go ahead.
Okay. Okay. Is it clear that this interaxis and this package alignment thing?
Yes, sir.
Okay. So I am sharing my screen again. Then we can discuss from there. Okay. So this part means we can.
Yeah, did you get it? What I've said?
Yes, sir.
Hello?
Yes, sir.
Madhu?
Yes, sir. Yes, sir.
Oh, acha. Again, all kinds of problem. You are talking in my headphone. Yes, Madhu.
Yes,
Did you get it?
yes, sir.
Okay. So this is the idea. Now you can go ahead. Yeah, Shrenjit, you can go ahead.
So the sensitivity data it is given in this data sheet. So how you will actually interpret this sensitivity data?
Give them 1 or 2 minutes to just think, because it's not so simple. They'll need some time.
Okay.
Yeah, let me revise this thing. Go ahead. Otherwise, nothing will get done. I don't know whether they will be able to say. Go ahead.
Okay. So your voice was breaking.
Yeah, so I'm saying that go ahead, because if we unless they respond, let's run through this at least. Otherwise, you will not have enough time.
Okay. This is the sensitivity to the measured input. Okay. So the measured input range we have already seen that this is from minus 3.6 to 3.6. Now.
not able to hear you. Can you hear me?
Yes, sir, we can hear you.
But not Sushanjit, right? I'm not able
Yes,
to hear.
yes. Yes, sir. He is getting disconnected in between.
Right. He's in hostel. He's in Kharagpur.
Hello.
So anyway, let's continue.
Yes, sir.
Okay.
Am I
go ahead.
audible now?
Uh-huh.
Yes, sir. Means some internet problem is there, so that's why. Okay, so this sensitivity is actually referring to that K term. Means in that the theory part we have seen that the output is equals to some Ki into A. So that K is referring to that sensitivity of the output with respect to change in input. So here it is that sensitivity. So from here you can identify that what is the minimum value and maximum value of output voltage if we are only considering the sensitivity. So this is the first part. Okay, the first part of the sensor modeling in static characteristics modeling. Okay, so other part is the sensitivity change due to temperature. So before going into that, I just want to go into this 0G bias level, because in the means this when we are seeing this sensitivity change due to temperature, so that means it is actually referring to some other inputs other than the measuring input. So the ideal sensors classification, the characterization, which is done by the sensitivity and the bias. So we will first look into that sensitivity and bias part. Okay, so the other part, that is the bias, that we will get from this specific.
Sir, you are not audible.
Yeah. So what he's saying is that this bias, this I think he's talking about this one, no?
Yes, sir.
So
Zero bias.
yeah, I see that the output is
Calculating all these things, we have to calculate we have to keep in mind that we have to calculate for in terms of voltage, even if it is given in millivolt, but we have to do those changes for voltage, because when we will see this sensitivity part, there these things will come again. Okay, is it clear?
now in between you dropped off.
Uh,
So this yeah. So sensitivity is 330 millivolts per G. So yeah. What did you? And this sensitivity may change due to temperature. Right. That's what you are saying. So it's a modifying input.
Yes, sir. But means this part I have not gone yet. Means I am now only now first trying to identify that ideal characteristics that is characterized by measuring input and the offset.
So the offset is 1 point. So the offset part you have to say that the offset is no.
Offset here it is given that 0G offset value is 1.5 volt.
So actually so what is the output range? Actually the output is 3.6 into 300 millivolts per G. So it's like 1 point plus minus 1.08 is the output, but there is an offset of 1.5. So it goes from, I think, what, 2.58 to 0.42. right? Rather 0.42 to 2.58. But 1.5 plus minus 3.6 into 0.3. Is it not? I think it will be better if you can use a board, Shrinjit. Is there a software board available? Is frequently dropping off. Okay, let me write. Let me write. This class is getting washed off. Shrinjit, can you hear me? No, I think he's dropping off. So let me present. It's a big problem.
Hello.
Yeah, you are dropping off. So I wanted to say hello.
Yes, sir. Yes.
So the input is plus minus 3 point. You can see my screen, right?
Yes, sir.
3.6
Yes, sir.
G. Sensitivity is 300 millivolts per G. These are nominal. So this output comes to plus minus 1.08 volts over the range. This is offset by plus 1.5 volt. So the output is 1.5 plus minus 1.08 volt is equal to 0.42 to 2.58 volts. This is the output range, right? Is
Yes,
this
sir.
correct?
Yes, sir.
So let me stop presenting. So yeah, Shiranjit, you are presenting.
Yes, sir. Okay. So the next part is that the sensitivity change due to temperature. Okay. So the sensitivity change due to temperature. That means here the temperature is acting as what? Is it a modifying input or interfering input?
Sir, modifying.
Yes. So as the here the sensitivity is changing, so this is acting as a modifying input. Okay. So from this specification, how you will calculate?
Impossible. Impossible. I think there has to be something. So that is also simple. That's not so difficult. Where is Shushanjit's screen? Here, right? Oh, can't see the screen.
Centigrade to 20 degrees centigrade.
Again, you dropped off. Again, you dropped off.
Oh, okay.
You are continuously getting dropped off. You can anticipate this. Yeah.
Okay.
Where is your screen?
Okay, sir, I'm sharing again.
Uh, where is the data sheet?
Okay. So the so here temperature is acting as a modifying input. Now the specification is given that it is plus minus 0.01% of per degree centigrade. Okay. Now in the question paper it is
0.01% of what? Can somebody say? It is 0.01% of what? Can somebody say this?
Sir, of 300?
Yes.
Nominal sensitivity.
Fantastic. Ranjit, show the page.
Yes. Again, I intro.
0 point,
Yes.
correct. So it's
Yes.
0.01% of 300. So what is the range of variation of the sensitivity? So it is 300. What is the maximum temperature variation? In this case, can we see what is the nominal temperature? I think 25 degrees centigrade, right?
Yes.
And what is the range of temperature mentioned? In
5
terms of
to
Kharagpur, 5 to 45, right? So what is the maximum change in temperature?
Sir, 20 degrees.
Right. So it's 0.3. It's 0.3 millivolts per G per degree centigrade. So now there are 20 degrees centigrade. So it's 6. No. 300.3 now, 0.03, because point was 0.01% and the value is 300. So the change is 0.03 millivolts per G, 0.03 millivolts per G per degree centigrade. And the maximum change is 20 degrees centigrade. So it's 0.03 into 20, which is 0.6 millivolts per 0.6 millivolts per G. So the sensitivity changes from due to temperature. The sensitivity changes as 300 plus minus 0.6 millivolts per G. Is this correct? Did you get it?
Yes, sir.
So now go ahead, Shiranjit.
Hmm.
The mistake is that you should be able to write. We have to address this in the next class. If you are not able to write, you cannot explain.
Yes, sir.
Okay?
Okay. Okay, so the other part is that here the change in offset versus temperature, this specification is given, that is plus minus 1 mg per degree centigrade. So here it is acting as a
mg means not milligram, it's milli-G.
milli-G, yes.
Yeah, that's why G is in italics. Yeah.
So here this temperature is acting as an interfering input as it is changing the offset. Okay.
So what was the offset? The offset, nominal value of the offset was what?
1.5.
Yes, 1.5 volt at the output. Here they are talking of variation of offset at the input. So for 20 degrees centigrade, it will be plus minus 20 milli-G is the offset. Now plus minus 20 milli-G means what is the voltage? What is the sensitivity? Sensitivity is what? What is the sensitivity? Volt output sensitivity. I think it's 300 millivolts per G, right?
Yes, sir.
Yes, sir.
So 300 millivolts per G is the sensitivity, and we are having plus minus 20 milli-G. So 300 into 20 divided by
6 into 10 to the power minus 6.
no,
Sir, 6 millivolts.
6 millivolts is more likely. So that's the offset error that can happen due to temperature. That is the effect of temperature as interfering.
but one thing here we have to note that here the sensitivity change due to temperature means where temperature is acting as a modifying input. So here this change, the percentage change, that is with respect to the measured value. But here this is means this is a fixed thing. So this is maybe this thing can be uh, 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 means quantified in terms of the full scale or span. Okay, because all the errors which we are calculating, we have to classify, means we have to categorize them as in terms of either the value or in terms of this error is in terms of the value. We can specify it because we are getting the sensitivity change in terms of volt per G, and here we are getting this as in terms of volt only.
Yeah, of course.
Okay, so I'm going to the
Yeah, the noise part. All kinds of problems today. Okay, so I will present, although I don't I'll get out the this thing out. Where is that? Here, tutorial sheet. No, we have to get the not the tutorial.
number 11. Okay.
Can you drop off, Sujanjit?
Yes,
Something wrong in the institute net today. Can you connect to a different net? I don't know how many are available.
I have tried with that also.
Right. So go to page number 11.
Yes, sir. Okay. Okay, am I audible?
You are, yes.
Yes. So here you can see that means the relation of the noise density with the RMS value of noise, that is given here, that RMS noise is noise density into root over of bandwidth into 1.6. So given the bandwidth and noise density, we can calculate that what is the RMS value of the noise. Okay. Now for a particular value of means RMS value of noise, we have to identify we have to estimate this peak to peak noise from this table, where actually from here you can see that if you are means taking the peak to peak noise, then the nominal value will exceed actually this nominal value.
Yeah, so you see that the RMS noise is given. What is the, so if you have a standard deviation of let us say sigma, is you can calculate. So then noise density is given in microvolts per hertz in the data sheet. Bandwidth you have selected, and so the total thing will become, I think, what is the bandwidth selected in our case? In the problem, what is the bandwidth selected? Can somebody tell me?
Hello.
Yes, you are back. I am just, whenever you are going down, I am stepping in. Go ahead.
Okay, so the means RMS noise we can calculate by using this formula, the noise density into root over of bandwidth into 1.6. The bandwidth is given in the problem is 10,
10.
and the noise.
Yeah. So it's basically 10 into 1.6 is 16, root over is 4. So it's 4 times noise density.
Yes. Now the thing is that from here we have to we have to take the peak to peak value, means we have to estimate the peak to peak noise, means how what is the interpretation of this peak to peak noise, that if you are choosing some peak to peak noise value, that means you are allowing some noise means to pass, means the percentage of time that noise exceeds this peak to peak nominal value, that will be decided by this estimated value. So if you are picking up a 2 times of RMS value as a peak to peak value, that means you are allowing 32% of time of this noise to exceed its nominal peak to peak value. Okay, so the nominal peak to peak value is this RMS noise, and if you are taking this as estimated value, then the 32% of time it will exceed. So similarly, if you are taking this peak to peak estimate as 4 into RMS, that means you are actually taking allowing 4.6% of time of that noise to exceed this nominal peak to peak value. So this thing.
Sir, how can it be that we are taking more time and it is getting reducing in time? Means we are
What
taking
is
more
it? No, that is yeah. Actually, you know what? What they see, it is saying that the percentage of time means basically probability. So the probability that a value is beyond plus minus 3 sigma or within 1 plus minus 3 sigma is what? Is 99.73%, right? That
Yes,
is the
yes.
property of Gaussian distribution. So probability that it is outside 6 RMS plus minus 3 means total peak to peak is 6. So that probability that the peak to peak value of the noise, the mean is assumed 0. That the peak to peak value is assumed to will be more than 6 times RMS is limited to 0.27% of the time, because the probability is 99.73, right?
Yes, got it.
Yeah. That's the idea. So if you, since it is said that with 99% confidence, therefore you can take the plus minus 3 sigma value. So it is 4 times noise density, and this is peak to peak, so maximum value will be 3 times that, 3 sigma. So it's 12 times the noise density. So now, Sriranjit, can you show the noise density? See, with this sort of an interpretation, you can get some estimate of what is the accuracy of the sensor, overall accuracy, due to temperature variation, whether you will put it in a temperature compensated package or not. All these decisions can be made only when you can make sense. So here you see it's 150 micro G per root hertz. So it's 12 times that. That means it's 1800 milli G, 1.8 milli G. Because it was 12 times, no? And if we are considering the Z axis, then it will be 300 into 12. 300 into 12, 300 into 12 is 3600 micro G. That means 3.6 milli G will be the worst case error due to noise. 3.6 milli G. That's another. So that is the noise performance. Yeah. Ranjit is out again, I think. So I think you can try this now, right? You can try this now. Will you take 5 minutes to, will you take 5 minutes to calculate it now that you have got? Do you want to put these together for 5 minutes? Just try. Priyanshu Verma,
Yes, sir.
so you can. Would you like to do it? Do you have a copy and a pen with you?
Yes.
So now that it has been explained, why don't you try? What is the total? What is the question? The question is what? Question is,
Try to calculate the total measurement error of sensor.
yeah, calculate what is the question? Let me read the question. Calculate specification of the total measurement error as X% of full scale output and Y% of measured output. So try that. There is component, calculate each part of the component and try to put them together. So 5 minutes, try that. If you have a question, ask us. Apply your mind for some time. Otherwise, if you want to do it, the class is for that. Then we can go to move into a new problem. We'll wait for 5 minutes, then we'll move into the next problem. Is this So what happened? Any progress? Moinak, कुछ किया?
Yes, sir, I'm doing.
वाह, wonderful. निशांत जी, साई निशांत कर रहा है ना कुछ? Nasari ji,
Yes, sir.
you're trying, right?
Yes, sir.
Wow. Thank you. If you are not having any queries, then you are progressing. We'd like to move on with the next problem. Do you have any question, Utkarsh? Utkarsh Agarwal ji? Hello, Utkarsh, can you hear me? Kushwa, Manavendra. Manavendra? Okay, let's progress with the next problem. Otherwise, we'll not cover anything. You can try it. Shrajit, let's see problem number 3.
Okay, sir. Huh.
Let them read it first. Put it on the screen, make the screen the largest possible.
Okay.
Slightly smaller, I think, otherwise they won't be able to read. I think we can read it.
But it is a big problem. Means anyway, we have to.
Now we can read this also. Yeah, this is also readable. Let's full screen. Full screen mode. Yeah, this is readable. So let's see up to this. Yeah. Where is this noise coming from? Shanji, the problem is gone. So read it. Similar thing. Read it for 2 minutes. So what's happening here? What is the block? What is the block diagram? There is a block diagram is they are giving overall specifications. What is the range? What is the range of the instrument? Can somebody say that?
The difference between the maximum input and output and minimum output.
That is called span.
Oh, sorry.
Range means range indicates generally maximum minimum values.
Okay.
So this 4 to 20 milliampere is the range. 4 and 20, these are the range values. And the span is 16. See, it is written as span is 16. And at zero pressure, the input range, there can be input range and there can be output range. The input range is some 0 to full scale pressure. See, this is a specification from a company, right? So the company measures manufactures many pressure sensors. So there can be, so that is why you will see that here, you come to the bottom, this burst pressure rating, come to the almost the bottom of the screen. There's, you can see that the instruments are available in many pressure ranges. 0 to 15 is a range, up to 0 to 50, then 0 to 100, then 0 to 20,000. So these are all different product lines of the company. So the same sensor cannot measure, if you make a same sensor cannot be used when the pressure varies between 0 to 15 and between 0 to 20,000, because the error specifications for them will be absurd. So therefore different, and then size, everything will be different. So therefore these specifications talk about various ranges. So 0 to full scale. What is the full scale value? Depends on the product range. In any case, for whatever is the full scale value, whether it's 15 psi or whether it's 50 psi or it's 100 psi, whatever is the full scale, the output is always going to be 4 to 20 milliampere at 24 volt DC. Is this clear? Some acknowledgement, please. Then what is read the span line. What do you think? What do you mean? What is being said? 16 plus minus 0.16 milliampere DC at 24 volt DC plus minus 2% adjustment available as an option means what? What do you think is the meaning of this line?
So Where 24 volt DC can go to maximum 24 plus 16.16 milli ADC.
No. 24 volt DC is the power supply.
Okay. Sorry. Oh.
You and any electronic circuit gain etc. will depend on power supply. So if the power supply, that is the nominal value of the power supply at 24 volt DC, the instrument is supposed to operate. But suppose you don't have, suppose you have connected two batteries but with 24 volt DC, then if the battery becomes old, that battery voltage will reduce. Does it mean that the instrument will shut off? No. So the instrument can, we will see later on, we have not seen the whole specification. Prosenjit, can you just go down please a little bit just to show? So you see the excitation is mentioned. The instrument works with 15 to 40 volt DC. So even if it goes below 24, it will work. But 24 is the nominal voltage at which the instrument is calibrated. So all the specifications that are told, now you can go up. So all the specifications that are being mentioned, the 16, 4, etc., they all hold at 24 volt DC. If the excitation changes, these values will change. How they will change is written below. So what is this plus minus 0.16? What is this plus minus 0.16? So you see, the company manufactures hundreds of sensors. So they are saying that if you take any number of sensors, the span will always be within 16 plus minus 0.16 milliamperes. But when you are using, let's say now you pick some particular sensor and you want to use it, then that may have a span of 16.1 milliampere. Because for an individual sensor, it may vary because there is component variation. So if you want to, either you should absorb this error and sort of, you should tolerate this error, or you can buy a slightly more expensive version of the instrument where there is an adjustment available. That adjustment 0.16 is what percent of 1600 or of 16? 0.16 milliampere is what percent of 16?
So 1%.
Right. So the worst case error that can happen is plus minus 1%. And you can buy a slightly more expensive instrument if you want to correct for the error. Then there will be, they also sell an instrument with an adjustment available. So that suppose the individual sensor that you have purchased has a span of 16 plus 0.16, you can reduce it, you can adjust it, and the adjustment range is plus minus 0.32. So even for worst case errors, you will be able to correct the span. Similarly for zero. So if you are willing, if you cannot tolerate this error, which can happen from from one sample to another sample in a batch, then you can buy an individual, so that before every measurement or for every sensor you can adjust. So there's an adjustment mechanism available whose range is mentioned. Similarly, you see 0.16 milliampere is what percent of 4? Yeah. What percent?
Sir, 2.5.
What?
4%, sir. 4%. 4%.
Right. So you see that because the worst case error is 4%, they have given a 5% adjustment so that you can correct for the worst case error. Then, so now you suppose you have purchased that adjustment wala sensor. then we can assume safely that it is the nominal span and 0 can be calibrated. So it will be exactly 4 and it will be exactly 60 at 24 volt DC. But still, there may be some accuracy problem, which is due to other factors, non-linearity of the strain gauge, non-linearity of the pressure diaphragm, whatever. So then the accuracy is given. So whatever is your straight line, in this case your straight line goes between 4 and 60, 4 and 20, exactly, because you have adjusted it. Then with respect to that straight line, let us say there can be I'm slightly changing the definition because otherwise the best fit straight line will depend on calibration data. But I am assuming that if we have adjustment available, then the best fit straight line, actually the best fit straight line goes through 4 and 20. Let's assume that. Then the nonlinearity is given within plus minus 0.25% of span. So what is the maximum error from this straight line at any point? What is 0.25% of span?
.04.
Is it 0.04? Yeah, 1% is 0.04, correct. So 0.04 milliampere is the accuracy specification, which includes the effect of everything. Hysteresis, in elastic elements there is a hysteresis problem. When you suddenly apply high pressure, it will expand, but when you take off the pressure, it will slowly decrease. So it will not decrease along the same path. So for increasing and decreasing pressures, you may get different readings. That's due to this property of elasticity. So anyway, the total accuracy is given. Resolution infinite generally means resolution cannot be infinite for anything, because you can only measure your measurement, whatever voltmeter or whatever you are measuring, it will have a limiting resolution, right? In the case of the accelerometer that we saw, there is a noise specification. So noise is random. So you can never, when there's an output change, you can never tell whether it occurred due to noise or due to an input change. So when they say resolution infinite, it merely means that the transducer mechanism is sort of continuous. Theoretically speaking, if there is a small pressure change, there should be a small strain, then there should be a small resistance change, which will be converted to a small milliampere change. So that is the meaning of when they say resolution infinite, they mean that. So, and then proof pressure rating is the pressure rating. This is very important because sometimes over pressure can come and it may damage the instrument. So they are mentioning that if you apply within proof pressure, then the instrument doesn't get damaged, and after removal of the pressure comes back to the accuracy range. But if you apply beyond proof pressure, which is 5 times the range in this case, then the instrument may permanently lose accuracy. If you apply more than burst pressure, which is here shown as 10 times the range, then the instrument may fail. I mean, some diaphragm or something will rupture and it will not work again. So these are safety things. Let's go down. What's the time? 35. We have time. Then, so that is the nominal thing. Now you come to all those interfering and modifying inputs. So the temperature range is, so now you see again this thing is coming. Temperature is again both a modifying input and an interfering input. So read this part. Go slightly down, then the excitation will. So So temperature is clearly a modifying and an interfering input because there is a sensitivity shift and there is a zero shift mentioned. But there is another such inputs, which is the excitation. See the excitation property. Span and zero sensitivity to excitation at the transmitter is less than 0.05% of span per volt. Per volt means per volt of what? Point 0.05% of span per volt means what? Per which volt is this?
So the 15 to 40.
Yeah, the excitation voltage. This power supply sensitivity. There is a for amplifiers there is a term called PSRR. You know that? There's something called CMRR, which is common mode rejection ratio. There is also something called PSRR, power supply rejection ratio. So this includes, this says the power supply sensitivity. So they are saying that the power supply sensitivity is 0.05% of span for span. Similarly, it will be 0.05%, as actually it's not mentioned, it should be mentioned that 0.05% of 0 for 0. 0.05% of span, it cannot be for zero sensitivity. So it's 0.05% per volt. Just like the previous case. Previous case also it was given something percent per milli G per degree centigrade. So like that it is taken. So now if you have, what is the worst case change of span due to, what is the worst case change of span due to power supply variation? Can you tell me? Worst case value of change of span for power supply variation. Worst case power supply variation. So what is the worst case power supply variation? Can you tell me? What is the
16 volt DC.
Huh?
16 volt DC.
That's correct. 40 minus 24. So if there is 16 volts power supply variation, and the span value we know is, it is 16. So it's 0.05 milliampere. 0.05 into 16 is what? It's 0.8. So it's 0.8 milliampere per volt. Now 0.05%. So it's 0.16 into 0.05. That means 0.008 milliampere per volt into 24. So 0.192 milliampere can be the maximum change in span due to power supply. Is this correct? My calculations? 0.05% of 16 milliampere is what? It's 0.008, I think, because 1% is 0.16. So 0.05% is what? 0.5 is 0.8. 0.5 is 0.8. 0.05 is 0.08. Oh,
So
it's
0.008.
0.08 per volt. So 0.08 into 24 is
Sir, into 16, right?
into 16. Correct. So क्या आ रहा है फिर?
0.128.
Is it 0.128 or is it 1.28? 1.28 is will be too much. 1.28 नहीं हो सकता. It's 0.16 milliampere. 1% of span is 16 milliampere. 1% is 0.16. 0.16 into 0.05 कितना होता है? 0.16 into 0.5 is 0.008. No, 0.08. And 0.05 will be 0.008, right? 0.008 into 16 is 0.128. What you said is correct. So 0.128 milliampere is the span shift due to excitation change. Once you understand the terms, it is the calculator there. It's just arithmetic, but you just have to need to interpret the terms. That's what we are trying to. That's what we have tried to impress upon you in this class. That if you see it, how to interpret the data, so that you can decide whether to buy an adjustment, whether what is the kind of error that can happen, whether you should go for temperature compensation. To able to assess that, how do you assess that from a given data sheet of a commercially available sensor? That's what we are trying to show you. Okay, so I think problem 3 you can try now, and you can do problem 4, 5 quickly if you have. This you, Sujanjit, can you explain, or Opro, do you know? Can you explain this? Anyway, they know. They have to calculate the Thevenins, but how to do that? But you cannot do that without. So see problem number 4. How do you find the V out? So either you replace the bridge by its Thevenin equivalent. You can write KCL, KVL also, but anyway, that's a bit naive at final year. Second year student can do that. But so how will you get the gain? For a differential amplifier with input resistance R1 and feedback resistance R2, perfect differential amplifier, the gain is R2 by R1. So in this case, the feedback resistances are given as NR0. What is the input resistance for a Thevenin equivalent of this bridge? Can you tell me? Because question says find the outputs for V equal to 10 volt, R0 equal to 250 ohm, N is equal to 100, and alpha is equal to, what is the gain? First, let us find out the gain. Output voltage we'll see. But for R0 alpha, you don't have to consider. So R0 equal to 250, N is equal to 100, and V is equal to 10 volt भी नहीं चाहिए, because that does not decide the gain. Just the gain of the amplifier of the circuit from output voltage from the error voltage which will appear across these two terminals to the output voltage. What is the gain of this circuit? Can somebody say that? Can somebody say what is the gain? we can, tell me if I'm wrong. Let me present. So, if can you see my screen?
Yes.
Hello.
Yes, sir.
So this part, if we replace by its Thevenin equivalent, this circuit will look like this. Do you agree? Do you agree? This is E0 open circuit. This is E0 Thevenin. Do you agree or not? So now you can imagine this to be a differential amplifier, and this is the EMF due to bridge unbalance, open circuit voltage. So what is the gain of this differential amplifier? You can find out. Okay? So this is what I wanted to say. So I am stopping to present. You can go back to the Shreya, I'm in a class. Let me finish the class, then I'll stop. Okay. So this is the thing. We can go back to the data sheet. Hello, Ranjit. Can we go back to the data sheet you were showing? I can show also.
Yes, sir.
So this is very simple actually. Tutorial will go below. Next one is also similar. That is even more similar. Problem number 7 is interesting. You can try it. We don't have time. We'll just explain so that. Where is this noise coming? So this is the sensor, temperature sensor, commercially available. This is not a short. The can see that the junction between the 220 ohm potentiometer and the R4 is not a short with the other line. That is not a short. That is so you can see that R2 is connected in parallel. So since the temperature variation of the resistance is given, you can it's pretty non-linear because it's a semiconductor sensor, and you can to some extent linearize it by putting a resistance in parallel which is of a very high value. That will linearize it and will overall sensitivity will reduce. So you are sacrificing sensitivity for linearity. And the rest of it, if you consider this to be a combination of resistances R2 and KTY, then it is a bridge again. And that bridge, in this case, the amplifier is a normal inverting amplifier. So you have to find out what is the potential here with respect to this. And again, the same Thevenin's concept will apply. So the gain of this amplifier will be, the feedback resistance will be 68 plus 4.7, whatever is the potentiometer setting. That will be the feedback resistance value, and the input resistance value will be 33 plus the source resistance, that is the Thevenin's equivalent of this circuit seen looking into this circuit. So that's how the gain has to be calculated. It's a slightly, it's interesting, you have to think about it. Then go down, Srinjit. So this is some data sheet things are given from for the sensor. Another similar question, simpler question is in 8, where there's a lead. We have discussed this, that is sometimes we connect a dummy lead so that we introduce an equal and opposite error for error correction. Then there is a 3-wire circuit. Go below. 3-wire. Then there is another bridge whose offset and sensitivity correction circuit is given. What is problem 10? We are problem 11 no, problem 13. 10. These are simple problems. 11, 12. Problem 13 is a very interesting problem which I figured out this time. The new problem. So it is a very special problem. If you can find out how to do it, it will be great. I think I'll really think if you can do problem number 13, it's more of a mathematical problem, but it's in an instrumentation setting. So if you can find the answer to problem number 13, then I'll be very pleased, because it's a very interesting problem according to me. All right, so we will stop here today, because time is up. So shouldn't you stop presenting? Yeah. So that's it for today. There was hardly any attendance because people cannot get up probably or whatever. But I hope, do you have any comments? Was this class useful? अरे कोई कुछ तो बोलो भाई. उत्कर्ष जी क्या ऑन करके घर चला गया क्या? Yeah, Mr. Agarwal, you are not there, I think. Okay. What about Priyanshu? Priyanshu?
Yes, sir.
Yeah. What? Yes, sir. Yes, sir. Kya?
Yes, sir. Like the class was useful, helpful in understanding things. Yeah, sure.
I'm looking for some appreciation, man, at the end of this. It's not so good. Thank you for your appreciation. Anybody else has anything to say? Otherwise, you can leave because you may have other classes. Thank you very much.
Thank you, sir.
All right.